Hi, I'm Greg Rosenthal, and I'm going to talk about interactive proofs for synthesizing quantum states and unitaries, which is joint work with Henry Yuen. First, I'm going to talk about state and unitary synthesis more generally, and then explain the interactive part. With state synthesis, the goal is to construct a quantum state, say given an encoding of that state as a binary string in some reasonable way as input. And examples of states that one might want to construct are quantum money, quantum pseudo-random states, etc. With unitary synthesis, the goal is to apply a unitary transformation to a given input register. And examples of unitaries that one might be interested in are variational quantum eigensolvers, decoders for quantum error-correcting codes, etc. And compared to what we know about the quantum complexity of decision problems, relatively little is understood about the complexity of quantum states and unitary transformations in general. So why are these sort of problems hard? Well, they can be seen as quantum analogs of function problems, where with a function problem, the goal is to map an input string to an output string. But there are at least three reasons that the quantum versions are harder. First is that there's no clear reduction to decision problems, whereas in a function problem, computing the output string reduces to computing each bit of the output string individually, which is a bunch of decision problems. But with constructing a quantum state, the output qubits could be entangled, so it doesn't work to just determine each output qubit individually. Second, because an n-qubit state has 2 to the n amplitudes, it's in some sense an exponentially more complex object than a string. And finally, in the case of the unitary synthesis problem, it's impossible to even describe the output state given unlimited time because the content of the input register is unknown. In this paper, we make progress toward an analog of the IP equals P space theorem for quantum states and unitaries. And what do I mean by this? We define quantum state and unitary analogs of well-known complexity classes such as P space and QIP. We prove that state P space is contained in state QIP, and as a partial converse, we prove that state QIP is contained in state X. We also prove that a certain special case of unitary P space is contained in unitary QIP. And we also obtain similar results with multiple entangled provers. These results are, of course, analogous to QIP equals P space and MIP star equals RE, and in fact reduce to these results as subroutines, but I want to stress that the reductions are non-trivial, as we will see. So first, let me define some of these classes. The model of interaction that we consider is as follows. There's a BQP verifier that interacts with an untrusted quantum prover over many rounds, and the messages are allowed to be quantum. Then the verifier accepts or rejects, which so far is exactly like the model of computation in the complexity class QIP. And then finally, and this step is different, when the verifier accepts, it also outputs a quantum state. And the completeness and soundness guarantees that we want to enforce are as follows. For completeness, there should exist an honest prover strategy such that with probability 1, the verifier accepts and the output state is approximately what it's supposed to be. And for soundness, for all prover strategies such that the verifier accepts with non-negligible probability, the verifier's output state conditioned on accepting should be approximately correct. More precisely, what I mean by approximately here is as follows. So for state synthesis, when the prover is honest, the output state is correct with an exponentially small error in trace distance. And for soundness, when the verifier accepts with probability any more than exponentially small, the verifier's output state conditioned on accepting for that prover strategy is correct to within polynomially small trace distance error. For unitary synthesis, we have similar guarantees, except that when the prover is honest, the output state is only correct within polynomially small trace distance error. So here are the classes that we define. State QIP is the class of sequences psi n n with psi n on n qubits that can be synthesized as above. Where generally one could consider state families indexed by binary strings rather than natural numbers. It doesn't really make a difference. We just need to consider some infinite family of states so that we can use asymptotic notation. And similarly, the requirement that psi n be on exactly n qubits isn't important. It could be polynomial in n, and our results would still hold. Unitary QIP is defined similarly, but with unitaries rather than states. State p-space, it's the class of state families that can be constructed in quantum polynomial space. And for purposes of this talk, you won't need to actually know what we mean by quantum polynomial space, but it's defined on the next slide in case you're curious. And then finally, the definition of unitary p-space is similar. So here's what I mean by quantum polynomial space. We say that CNN is a family of quantum polynomial space circuits if these three conditions hold. First, there should exist a p-space machine that on the all ones input outputs the description of C sub n. Second, C sub n should consist of the following types of operations. First, it's allowed to apply gates from a universal gate set. Second, it can measure qubits in the standard basis. Third, it's allowed to trace out qubits. And fourth, it's allowed to introduce new qubits initialized to the zero state. And finally, we require that at any given point in the execution of Cn, it uses at most poly n qubits, which is why tracing out qubits above is important. So first, let me talk about the proof of state p-space in state QIP now, and then I'll talk about the proofs of the other results. As an easier problem, or as a warm-up, let's consider state synthesis with a trusted prover, but assuming that prover is only allowed to send classical messages. And the solution to this problem is due to Aronson, and we can construct an arbitrary quantum state in this model in polynomial time as follows. First, let's write the target state psi as beta 0, the 0 qubit, and some state theta 0, plus beta 1, the 1 qubit, some state theta 1. Then the verifier will query the values of beta 0 and beta 1 to finite precision. The more bits of precision, the lower the error. To get exponentially small error, it suffices to query to poly n bits of precision. Then the verifier will construct beta 0, 0 plus beta 1, 1. Let's say for future reference in a register that we'll call R. Then the verifier will uncompute the values of beta 0 and beta 1, again by calling the oracle. I'll explain why this is important later. And finally, controlled on the bit I in that previously mentioned register R, the verifier recursively constructs theta I, which will yield psi. So why is it important to uncompute beta 0 and beta 1? Well, at the outermost level of recursion, it doesn't really make a difference. But otherwise, if we don't uncompute the garbage, then if we write the target state psi as some overall n-bit strings x of alpha xx, if we don't uncompute the queries, we would instead output the first n qubits of some x, alpha x, x, some garbage state depending on x, which is not what we want to do. So now, how can we transfer this or convert it to a protocol with an untrusted prover, but who's allowed to send quantum messages? Well, for states that are in state p-space, it turns out that the queries from the trusted prover protocol can be computed in p-space. And we prove this using p-space equals BQ p-space and algorithms for quantum state tomography. So this yields the idea, what if we run the trusted prover protocol but answer the queries using the IP equals p-space protocol in superposition? And the issue with this, like it does prevent against certain attacks by the prover in the forward direction. The issue is when in the step where we uncompute the queries, where we run IP equals p-space in reverse essentially, which we need to do. Because then we need to make sure that the prover also uncomputes honestly. So for example, here's one attack that the prover might do on this protocol. let's say it's, for example, honest until the very last round. It's honest in the forward direction of IP equals P space in the last round. But then controlled on the classical string X, it constructs some state phi sub X in private. And then which it's not supposed to do. And then after that, it just uncomputes as normal. Then the verifier would output the first n qubits of the state sum x, alpha x, x, phi x, where phi x is held by the prover. And that's not the same as outputting psi. So how do we fix this? First, let me introduce some notation. Let psi sub k denote the k qubit state that the verifier obtains after k iterations of the trusted prover protocol. So for example, psi sub n is the target state that we want to construct, and psi sub 0 is just like the 0 qubit state. Given two copies of psi sub k, let's call them copy 1 and copy 2. Here's a procedure that will allow the verifier to obtain two copies of psi sub k plus 1 in a verifiable way. And then by doing this for k all the way up to n, that's how the verifier obtains the target state. So the verifier will first flip a coin, and it's very crucial that this coin is flipped in private. The prover does not know what value this coin is. We'll see why that's important later. If the coin comes up heads, the verifier will do a procedure described on the next slide that should ideally yield two copies of psi k plus 1, if the prover is honest, that is. And if the coin comes up tails, the verifier will do a procedure that should just ideally end up back where the verifier started with two copies of psi k, but might detect dishonest behavior by the prover in the meantime, which is the point of this. And then we just the verifier keeps flipping coins like this until one of them comes up heads, and that's how we progress to psi k plus 1. So now let me go into more detail here. In the heads case, the verifier will simulate a round of the trusted prover protocol on copy 1, which recall that this should yield psi k plus 1 if the prover is honest. Then let's say the prover was honest. Then when we request a second copy of psi k plus 1 from the prover and do the swap test, the swap test will pass. And the prover is forced to be honest in sending that second copy of psi k plus 1 here, if it was honest so far, because otherwise the swap test would detect these two states are different. Now for the tails case, the verifier is going to start off by behaving exactly like it would in the heads case, as far as the prover can tell, i.e. it simulates a round of the trusted prover protocol on copy 1, but the verifier just leaves out the step in the middle that grows the state by a qubit. Recall that I mean this highlighted step right here. And if we leave out this step, then everything is just uncomputed. And so it should yield psi k back again. That's if the prover uncomputes honestly. But if the prover doesn't uncompute honestly, the resulting state will be different from psi k. So then when the verifier does the swap test with this copy 2 that we had originally, it'll detect that the prover was cheating. So to recap, the tails case, it forces the prover to behave honestly when uncomputing. And since the prover doesn't know whether it's tails or heads until after it's over, that forces the prover to be honest in general, essentially. Now this protocol will work, but with a weaker soundness guarantee than we would like. So we finally amplify the soundness of the protocol as follows. We execute that protocol polynomially many times. If any one of those executions reject, then we know the prover was dishonest and we reject. And otherwise, the verifier will accept and output the output state of a uniform random one of these executions. And the intuition here is that it gives the verifier more opportunities to detect the prover cheating. Now I'm going to go over the proofs of these other results. First, the inclusion of state QIP and state exp. The state exp machine will find an approximately honest prover for the state QIP protocol by optimizing over an SDP. The variables in this SDP will be the density matrices held by the state QIP verifier at the beginning and end of each round. The constraints in the SDP will enforce that the start state is correct, the transitions between rounds are legal, and the end state is accepted with high probability, which this argument is analogous to the original proof that QIP is contained in EXP. And then once the state EXP machine has a description of an honest prover for the state QIP protocol, it can simulate the state QIP protocol with that prover, resulting in the output state of the state QIP protocol. Now for a special case of unitary p-space contained in unitary QIP, we say that an n-qubit unitary U has polynomial action if U acts non-trivially on a subspace of dimension at most poly n. And this is proved using a Hamiltonian simulation algorithm. So more precisely, if we write the unitary U as e to the it rho, where t is some time and rho is a density matrix, and if U is in unitary p-space, then we can show that a certain purification of rho is in state p-space. So using the inclusion of state p-space in state QIP, which we previously proved, the verifier can obtain copies of rho. And additionally, the evolution time t of this Hamiltonian, we showed that it's computable in p-space. So using its p-space equals QIP, the verifier can obtain the value of t. And then given t and given copies of rho, implementing U can be done using this Hamiltonian simulation algorithm. So where does the polynomial action assumption come in? If we assume that U has polynomial action, then the evolution time of this Hamiltonian is at most poly n, and this is necessary for the Hamiltonian simulation algorithm to be efficient and to require at most a polynomial number of copies of rho. Now here are the analogous results with multiple entangled provers. We define state R as the quantum state analog of the class R of computable languages. And this is the class of state sequences, one on each number of qubits, such that descriptions of exponentially good approximations of these states are computable as a function of n. And I'll explain why it's not state RE in a moment, when we prove that state R equals state QMIP. So for the inclusion of state R in state QMIP, it's just like the proof of state p-space in state QIP that we previously went over, but using MIP star equals RE in place of IP equals p-space. Then for the reverse inclusion of state QMIP and state R, this is done by brute forcing over all provers until an honest prover comes up, and then given an honest prover, just simulate the state QMIP protocol to construct the state. And this is where the quantum state version of the statement is not directly analogous to the decision problem version of this statement. Why? It's because if you try to prove that R equals MIP star using similar reasoning, which is a false statement, and but if you tried to prove it using this reasoning, the problem would be that the search would fail to terminate for strings not in the language. But by assumption, like by the nature of our model, we just assume that an honest prover exists. So the search always terminates. And finally, using similar reasoning, we prove that, quote, polynomial action unitary R is contained in unitary QMIP. Open problems. There are a lot. First, recall that we proved state QIP is contained in state X, but can we improve that the state QIP is contained in state P space, which would imply a complete quantum state analog of the IP equals P space theorem. Second, some of the errors on our results were polynomially small. Can we improve them to exponentially small? Can we reduce the number of rounds in our protocols? All of our rounds have a polynomial number of rounds, but can we get it down to constant? We do propose constant round variants of our protocols that we conjecture to work, but we haven't proved that they work. Is it the case that unitary p-space is contained in unitary QIP? Not just that polynomial action unitary p-space is contained in unitary QIP. Can we generalize our protocol to construct mixed states rather than just pure states? What about state and unitary synthesis if we require the provers to be efficient? Currently, our protocol requires the prover to solve problems in p-space. What if we consider multiple unentangled provers rather than multiple entangled provers? Interestingly, some of our results break down if the provers are unentangled, in particular, soundness amplification and the tomography step. And finally, is there an interesting notion of zero knowledge for quantum state and unitary synthesis? And are there cryptography applications? Thank you.